Hello, everyone. Welcome to this webinar, uh, SolidCAM 5-axis simultaneous milling. That's how this entire webinar is going to be about. About the webinar, this webinar will be of a minimum of 90 minutes, in which I have divided it into two halves. The first half basically will focus on 3+2 and generic milling of SolidCAM 5-axis. The second half will focus ourselves on the application-based machining strategies inside SolidCAM Simultaneous 5-axis. It could go about 10 to 15 minutes here and there. So please patiently bear, because it's a pretty vast system. So there are a lot of areas that I need to show to you. So it's going to be a slightly lengthy webinar, but not as lengthy, and I'll make it sure that it's pretty interesting. Okay, so let's start off with our presentation first. So today's session is going to be about the agenda. Basically, is going to be about SolidCAM 3+2. I'm not going to spend much time on this. It's 3+2 milling for the initial few minutes. Then it's going to be the output types. Basically, when in 3+2 you have got several output types. One is using the 3D coordinate rotation function. The other one is possibly when the machines don't have the option of 3D coordinate rotation, then we use the macros for calculating the coordinate system shift. And the next one is by outputting using a pure angles, where macros are available, but the operator or the users are not comfortable using the macro functions. They would not like to have several calculation routines being called. They want a simple XYZ with the angles. So we call them as a pure angle method. These are the three important methods that we are going to see today. And then we will jump to the generic 5-axis milling, where we are going to see some very interesting paths. The first one, of course, is going to be a pretty basic and simple one. Then we will move into a turbine blade. How do we machine a turbine blade using the generic 5-axis functionality? And then we will move into a closed impeller and see how a closed impeller gets machined using the generic 5-axis functionality of SolidCAM. Once we have done with our generic 5-axis functionality with basically these three parts, we will move into the application-based machining functions like screw milling, impeller milling, port milling, swarf machining, multi-axis drilling, multi-axis machining. So we're going to see a lot of stuff in the application-based machining strategies. I'll also explain to you what these application-based machining strategies are, so that it's clear to you what exactly to expect. All right. SolidCAM 3+2 basically enables efficient, profitable machining of multi-sided parts on 4 or 5 axes. So you can call it as a 3+1 or a 3+2 machining. And with the easiest coordinate system, you're going to see that you don't actually need to define any coordinate system today. So you will see how we work very, very easily. Not a lot of training is required, probably 1 or 2 hours of training, and we are done. The 3+1 and 3+2 training is basically, the 3+1 and 3+2 machining is basically for enabling flexible setups, and it reduces the need for special clampings and jigs that are needed. And the most important thing, like I said, we output the 3+1 and 3+2 in several methods. One is using the 3D coordinate rotation functions of the controller itself. The second one is using the macros. And the third one is just by outputting pure angles, where the controller doesn't do anything. And the entire shift calculation is being done by SolidCAM, and the coordinates of the shift origin are output directly to the control. So the outputs are basically ready to run G codes. You don't need to do any modifications, nor do we suggest any modifications to be done once the output is done. Right. So let's look at the first output type in the 3D coordinate rotation. Excuse me. We told that there is an issue with the audio, so I would like to. Is my audio clear now? Okay, sorry. So we will move into the first 3+2 function using the 3D coordinate rotation. And this is with Fanuc. So with Fanuc, we use a function called G68.2, where we output the earlier the shifted location, and then we output the rotation angles, and then we tell to the control that you need to rotate the tables, basically. The next one is Siemens, where we use the cycle 800. And this cycle 800, we again output using the 16 variables that are there in the controller, and this output comes directly from SolidCAM itself. So we use cycle 800 inside Siemens. With Heidenhain, there are two variants. There is Heidenhain. It's Heidenhain the TNC 530, where we output the rotation in two functions. One is first moving the origin using cycle 7, where we shift the origin basically in X, Y, and Z. And then we use the plane spatial function to rotate the coordinate system itself. So there are two functions, cycle 7 and the plane function. Right. So like I said, Heidenhain has got two variants, the 530 variant, and it also has the 426 and 430 variant. In the 426 and 430 variants, these are basically the older models of Heidenhain. We again output using two functions. One, the cycle 7, basically the shift of origin, X, Y, Z. And the other one is using cycle 19 and cycle 19.1 to rotate the coordinate system. Okay, so there the plane function doesn't exist in the older controls, but the function is done, or the rotation is done using cycle 19 and cycle 19.1. So these were the three common controller functions that you could encounter. There are several other controllers, but I'm not touching upon them. I've just picked up the three most popular controllers. That's Fanuc Mitsubishi, Siemens, and Heidenhain. Heidenhain, both 530, 426, and 430. Another very important function is that the older generation controls of Fanuc, they do not come with the rotation, 3D coordinate rotation. Basically, it is the G68.2 functions are not there. G68.2 functions are not there, but these controllers, or probably the customer has not brought this option. These controllers, we send what we call as the B macro, or the macro calculation, where we do both the shift of the coordinate system and also the rotation coordinate system, rotation coordinate system calculation using a B macro inside Fanuc. Somebody asked me to explain Fanuc again, I'm sorry. So in Fanuc and Mitsubishi, if there are new generation controls or you have bought the option on Fanuc, then you have a function called G68.2, which is actually doing the coordinate system rotation. Okay, this just single one line will do the coordinate system rotation. However, there are several times where the customer either is not aware or this function is not provided as a part of the standard option inside Fanuc, or they have an old Fanuc control. In such controls, we use what we call as the macro functionality. Macro is basically standard inside Fanuc. And in macro, we output two programs. One is the main program from where we call the macro, and the other one is the macro calculation itself, which does basically the shifts and the rotation calculation. So what we do basically is we set G54 on the machine, and every time there's a rotation and it needs to go to another plane, it writes into the tool of in the work offset, it writes a new G58 coordinate system, and it calls the entire program, or it runs the entire program for the new G58 coordinate. Okay, so this is basically a macro, but many times macros are not easily readable by the users nor by the operators. So I have several of my customers who hate this macro, although macro has great advantages. Okay, the biggest advantage is macro functions exactly similar like G68.2. What is the biggest advantage? The biggest advantage is that you could position the part anywhere on the table. You could have done the programming using the center point of the table as your reference, but on the actual machine, you could position the part anywhere on the table and you could run the same program. So even if you're doing mass production, you could put one part in the center, the second part need not be in the center. It could be shifted away slightly, no problem. You put that set G54, call the program. The macro will recalibrate the new position. So you don't have to go back and regenerate any new programs. Okay, so this is the biggest advantage that you get either with G68.2 or with macro. But like I said, there are several of my users and operators who don't like, because they feel it's very complicated, although they don't really have to do anything. They feel it's pretty complicated, and they can't understand what is happening, which is fair. So in such cases, we go to another function, and that's called as a pure angle function. In a pure angle function, basically we expect, or we assume, that the controller is not going to do any kind of calculations. The controller is simply going to move the machine to the coordinates that the program asks it to go. So all those shifts and rotations have to be calculated by the CAM software, and then the G code needs to be sent. The calculated G code needs to be sent to the machine, and the machine will simply move to those coordinates, or the controller will move the machine to those coordinates. It will rotate and it will move to the new coordinates. The advantage here is that the operator and the user can actually see the program and they can visualize the program, what is happening. Okay, but there's a big disadvantage to it. The disadvantage is that since you're doing all the calculations by yourselves inside the CAM system, you expect, or you have to put the part at the same position where you assumed it to be before calculating inside the CAM system. So if the position of the part changes on the table, you have to come back to your CAM system, re-enter that position, generate the G code, and take it back. So this is a major disadvantage working with pure angles. But many of my customers are okay with it because they are using the fixtures or jigs where they say that the position won't change more than 5 to 7 microns or 5 to 10 microns, and they are fine with it between two parts. But the most important thing here is a visualization. The operator becomes comfortable looking at the program. He knows where the machine is going to move, where it is going to cut. He has complete idea because it's like reading a simple G code. So this is a pure angles function. What I will do is I will move away from my software, from my presentation, and I'll go into the product. Sorry. I think I clicked something else and it would come up now. Yes. Let me just, yeah, let that be there. So I have a part, and the first function that we're going to see is for Fanuc. Okay, so I have called in a Mazak MultiAxis 500, which is a table kind of a machine, and it has got its own muzzle troll control, which basically is very highly compatible with Mitsubishi and Fanuc kind of programming. So it's going to be very similar to Fanuc. So I would now like to create some programs here, which are basically from different sides, and I would like to post-process and check the output. So I'm going to use the same part and show you the difference between moving from Fanuc to Siemens to Heidenhain to macro to pure angles. And I'll also show you how to check your part program, especially in the pure angles function, where you don't know how the machine is going to move, how to check that right away into your system and confidently give the program down to the machine. So I'm going to use my drag and drop templates. I have got some facing templates here. And since I would like to do some facing programs, I want to apply some facing templates. So I'll use a simple drag and drop. I have a 3+2 with a 32 face mill. This program was already done on some other part. I just saved that particular program as a template. I'm just going to drag this and drop it on the face here. And I get the program. Now, the part of this drag and drop templates on side faces are that I don't need to create any coordinate system. The coordinate systems are created within the templates when they are applied to the face. For example, I can just drag it and drop it on this face. You can see that immediately it creates a coordinate system for that particular face, and the program is created. Similarly, I'll just drag and drop it onto this face, program generated, drag, drop it, sorry, drag, drop it on this face, program is generated. Again, drag, drop it on this face, and the program is generated. Okay, so I've got 5 programs rather, for the 5-side, what we call the 5-side milling. Right. Now we'll also look at some very quickly, some other areas also. For example, I want to machine this chamfer. So since I'm using a big tool, I just want a single pass. So I have got another template for single pass. I just drag and drop it on the chamfered face. You can see the coordinate system is already created, and it just creates a single pass to machine the chamfer. Fair enough. These were to be calculated. Let's calculate. Okay, so I have my program. So if I now output the first program, which is basically nothing but a simple pure 3-axis kind of a program where it's not going to do any tilting, you can see that I don't get any G68.2 function because it doesn't need. It's a simple 3-axis XY plane machining. Okay, so it becomes a simple 3-axis program. But if I take the next one, the single pass program, and if I just generate a G code out of this, okay, you'll see that it outputs the G68.2 function where it'll output P1, the Q123, basically the rotation priority, X first, Y next, Z next. Then the X, Y, and Z. These are basically my coordinate system shifts. How do I get my coordinate system shifts? I simply go into my coordinate system and I click on inquire. And if I go here into my translation, you can see here is that it is shifting by X minus 54.09, Y 0, and Z minus 38.196. That is the position where the coordinate system is with reference to the main coordinate system. So this is my coordinate system, and the reference is with reference to the main coordinate system. Okay, so if I look at the program, I get those 3 coordinates. So basically, I'm telling to Fanuc, or I'm telling to the controller, move first to this position and then rotate around X-axis by minus 80 degrees, Y-axis by 0 degrees, and around Z by 90 degrees. Once it does that, it achieves the position that is needed to machine it, and then G53P2 will rotate the tables, both in A and C or B and C, whatever those axes are. It will rotate the table, and it will run the program. Okay, fair enough. Let's change the controller. From Fanuc, I'm going to keep all the programs same. I'm going to move to Siemens 840D. So I'll go to Siemens. Okay, here. Done. And the same program, the same single pass program, I'm going to generate the G code. Okay. So instead of G68.2 or anything else, I'm getting cycle 800. Okay. Now cycle 800 has 16 variants, out of which 14 are must define variants and 2 are optional. You could define or you could not define because they can be taken as defaults. And each variant has its own special place. For example, like I said, 54.090 and minus 38.96, you can see those 3 values coming up. And then we have a number called 27. We have got 54. So basically these numbers tell you the priority of rotation. Okay, if you go to Siemens manual, you will know that one particular number, it will be ZYX, the other one will be XYZ, the other one will be YXZ. So the priority of rotation is defined by these angles. Okay, so this is about Siemens. So we get an output like this for Siemens. Let's go to Heidenhain. I'll change it to Heidenhain. Let's take the DMG 65 monoblock with ITNC 530. Now the window that came up to me, which was asking me something, was basically telling me that the cycles between Siemens and Heidenhain are not the same. So please map the cycles. Okay, the CAN cycles. Okay, let me take the second program again, generate the G code, get the output. So you can see that I have cycle 7, 7.1, which is basically shift in X, 7.2 shift in Y, and 7.3 shift in Z. And then I get the plane function where I rotate the angles based on rotation around X, rotation around Y, and rotation around Z. And I turn the table by a certain feed and take the position and wait for the program to start. So these are like straightforward methods. Not much. The operator and the user can get a lot of clarity on what is going to happen. Like I said, macro gives you the same functionality, but however, it looks very complicated. So let's look at a macro function. Let's load a AMS machine. This is with Fanuc. Yeah. Say okay, continue. Okay, 5-axis is basically 54, and this one is G65. Okay. So I'm going to change the submachine to indexing. Okay, and let me, before I go into the generation of G code, there are two files, like I said, that get generated. One is the main file, which has got the program as well as the macro call. And the other one is basically the macro calculation itself. The macro calculation need not be output every time from the software, because you just take the macro calculation once for that particular machine, put it into the memory of Fanuc, okay, not anywhere else, into the memory. It has to reside into the memory. And once it is inside the memory, you need not output that macro call again and again for different parts. It stays there forever unless you change the machine. Okay, so I'm going to output the macro for the first time. Say okay. And the same single pass program, I'll generate the G code now with a Fanuc output. Okay, so you see that you're getting two programs here. Okay, let me explain these programs to you because they're pretty interesting. First of all, this is my main program, wherein it calls, using the GA65 function, it calls P8889. The P8889 basically is the same 8889 macro call calculation, or it's a macro calculation. Here I output to the controller the X, Y, Z positions, the changed positions of my basically the shift of the origin. And I also output the B and C angles to the controller. But this is not enough. Just shifting the origin and rotating the B and C angles are not enough. I also need to move the origin physically inside the controller. To move that particular origin physically inside the controller, I use the macro call function, or the macro function. The macro function basically is a combination of several mathematical functions, trigonometric functions, which will use the cos and sine methods to generate the new shift and the new coordinate system, which basically is going to be our new G58 every time we call the program. So if I output, for example, not one, but let's say, close the programs. Let's say 1, 2, and 3. If I output these three programs together and generate the G code, I'll get only one macro call. I don't need that. But here I can see that for the first toolpath, there is one macro call. I go down. For the second toolpath, there's another macro call, because here it's going back to the home position. resetting everything, and then recalling the macro again. Once this program is executed, it again goes back to the home position, resets everything, and calls the macro again for the next program. So every time there is a change in your coordinate or a plane, basically you go from one plane to the other plane, a new macro, the macro is called again, and a new G58 is set, and always the programs will be executed from that particular new G58. So like I said, macro offers great advantages to those controllers which do not have the 3D coordinate rotation function. Now, in SolidCAM, we support macros both from Fanuc as well as Siemens. In Siemens, we use the R parameters for programming the macro. In Fanuc, we use the hash parameters, which is the B macro. But looking at the program, sometimes the operator, their eyes will start rolling around because they find it very difficult to comprehend unless the operator himself has not been trained on the macro. They dislike the macro functions. So in such cases, we have to change our programming method, and we need to go into what we call as the pure angle method. So I simply switch the sub machine inside the machine itself, and I go from a macro method to a pure angles method. Now, what I'm going to do is I have entered the part position, basically. So I have got my G54 here, and my G54.1 P1 will be exactly at the center of this bore because that's the mating part on my table. Okay, so I go to the machine, I set G54.1, I mount the fixture and the part, set my G54, and I get two coordinates, XYZ, XYZ. And I do a subtraction, and I find the difference between G54 and G54.1, both in X, Y, and Z. And those values, I come back into SolidCAM and I enter here. Because remember, the controller is not going to do any kind of calculations. The calculations will happen by SolidCAM. So I bring the values, I put the values here, okay? If you want, you can just look at where the part is going to be stationed at, okay? Not in this case. Once these values are done, say, okay, let's generate the G code. Now this is going to be generated not with reference to G54, sorry, macro is not needed here, but it is going to be called with reference to G54.1 P1. Okay, so all my coordinates are now going to come with G54.1 P1. Okay, so you can look at the values. The values look crazy, but if you ask the operator can visualize very easily. So what we will now do is we'll go into the machine simulation and we'll check if our G code with respect to the machine is okay or not. You don't even need to go and take it to the machine and then get some surprises. It's not needed. You can check it 100% here itself. Now, before we take it into the machine simulation, I would like to note down one value here. Go to the tool, and I will note down my edge length, which is basically the tool edge length, 122. Okay, so let's go into the machine simulation. And let's look, this is on an AMS machine, and you can see that it's ready. And if I run the simulation, this is how it's going to run. One pass, second pass, done. Okay, so let's go back. Now we are ready here. Now I look on the side here. Okay, I get a coordinate of X, Y, and Z. The B angle, the C angle, and the B angle. Okay, now this X, Y, and Z are basically the machine coordinates. These are not the coordinates coming from G54, but these are machine values. So I now need to verify if these machine values are the same as my G code values. So what is my X value here? It's minus 254.344. My Y value is 71.20. First, let's check if we are getting the two X and Y values same. Okay, so we have minus 254.344 and Y 71.200. I can now be 100% sure that my X and Y values are absolutely right. It's going to come to that position. Now the problem is of the Z value. The Z value here, the first value is 50.058. This is where the tool is going to come and stop after it calls the G43 function. That is after it takes into account the H length, which we have defined in our software as 122. So that same edge length will be transferred to the machine simulation also, not to the machine, but to machine simulation. So let's look at the H value, the Z value here. It's 172.058. Okay. Now we have how much was our, it was 50.058, whereas here I'm getting 172.058. So let's take to a calculator. Let's take 172.058 minus the H length, which was 122. Let's see if our G code value is right. Oh, my G code value is also right. So the Z value of 50.058 is also perfectly okay. So I have now cross-verified my G code with reference to my machine. So I can just blindly take this program, go to the machine and run the machine 100%. It's going to run, provided your pivot calculation that you have done, pivot finding calculation that you did on the machine was exact. If your pivot is right, you don't have to worry. This program is going to run on the very first attempt on the machine. No need to do any kind of other calculations there. Okay. We have got a special training course only for this 3+2, especially for pure angles. Okay. Someday we could have just a session for this particular, because it's pretty interesting. And there are several machines today in India that do not have the 3D coordinate rotation functions, neither they use the macros. So the only way we go here is with the pure angle method. Okay, so many of my customers, by the way, are using this method successfully. They don't look left, right. They just take the program down on the machine and run it. Right. So that was about 3+2, not much. We saw some 3D coordinate rotation functions. We saw the macro function, and we also saw the pure angle functions, including checking the machine. Let's get back to our presentation, and let's go ahead with our presentation. Move ahead. We're now moving into the simultaneous 5-axis, which is basically the generic. Okay, we are going to see the generic functions. It's a very powerful simultaneous 5-axis, generates very powerful simultaneous 5-axis toolpaths with a very user-friendly interface. You'll see that it's very, very easy. Collision check and avoidance for tool holder and other machine tool components are provided within the software. And then apart from that, we have the specific application solutions for swarf, multi-blade port, contour, multi-axis drilling, conversion of 3-axis to 5-axis, etc. And we can simulate the entire machine tool, including the material removal simulation, showing both the rotational and linear axis. Now, one word about generic 5-axis. Generic 5-axis is a vast system. Okay, you will see that it's a very vast system, and there are no parts that cannot be done on generic 5-axis. Everything is possible. Okay, only thing, because it's not an automated function, it could take some time to get adapted to a new part. But apart from that, it can machine any part, whether it's a port, whether it's an impeller, whether it's a blade, whether it's a part, whether it's a drill, anything. You throw anything at the generic 5-axis and it could do it very efficiently. Okay. Generic 5-axis basically has 3 components to it. The first component is the strategies. So we have got many strategies, parallel cuts, which is basically constant Z, parallel to X, parallel to Y. Then we have parallel to curves, parallel to surface, perpendicular to a curve, morph between 2 curves, morph between 2 adjacent surfaces, projection, basically for engraving in 5-axis, user defined. You could do radial, you can do spiral projection, and you could also do offset projection. So these are the main cutting strategies inside the generic 5-axis function. So one component is the cutting strategy itself. The second component is the tool axis function. The tool axis function is the most critical function inside 5-axis, okay, because that will control your entire tool path, that will control how you machine a particular part on a machine. SolidCAM has got a vast array of tool axis controls. Okay, so you have got always normal to the surface, relative to the cutting direction, tilted to a surface normal by an angle, tilted to an axis by a fixed angle, rotated around an axis, tilted through point, tilted through curve, tilted through lines, tilted from point away, tilted from curve away, tilted relative to machining impeller layer, and tilted relative to contact point. And each of these functions then have got sub-functions within them. And these sub-functions help you to control the tool even more effectively than just providing a main function, okay? So the second component in generic 5-axis is the tool axis control itself, which is the most critical functionality in 5-axis. The third and the most other important functionality in generic 5-axis of SolidCAM is the gout check. Again, we have tons of different methods of gout check. Now, one of the most important aspects of gout check here is that in SolidCAM, you can put 4 different reactions, okay, to a particular gouge. For example, if I go back to this particular part here, okay, you can see the part on your screen on the right-hand side. I have got some surfaces here, some surfaces here, some bottom surfaces, okay? Now I can put a different reaction to this group of surface. I can put a different group of reaction to this particular group of surfaces. I can put a different reaction to this surface groups, okay? Different reactions if it finds collision. For example, for this particular surface group, I could say just tilt the tool to this particular group. To this particular group of surface, I could say you just trim the tool path, trim the collisions. And to this particular group of surface, I could say retract the tool up, okay? Just retract the tool up. So I can, in just one small part, I have now defined 3 reactions, okay? It's just not, you select a surface and say gout check. The software needs to know what to do if it finds a collision. That's what we call as reactions. And here, in one single small part, I put 3 different reactions to it. Tilting to one group, trimming of the tool path to the other group, and retracting from another group, okay? So you can put in SolidCAM 4 such groups of surfaces and 4 reactions to these surfaces. So these are the gout check strategies we have. We have retract the tool. Again, in retract, you have got plenty of sub strategies of retraction. Then we have tilt tool, where we can tilt in the lead lag fashion. We could tilt in using the side tilt method, or we could use the automatic function and tilt, where it will use a combination of both side tilt and lead lag and apply a special tilting mechanism to avoid a collision. And then we have trim and reeling. Again, then we have sub options. So our way of working in SolidCAM is that we first define the strategy, we define the tool axis control, we define the gout check, and we calculate the tool path. So this is a simple streamline. Now, this is a flow of the way we generate the tool path. Like I said, generic 5-axis is very vast. So is the support of the tools that we have in generic 5-axis. We have got end mills support, we support bull nose, we support ball nose, we support face mills, we support dovetail mills, we support taper mills, flat taper mills, we support taper ball nose, we support slot mills, we support lollipop, and we also support the new generation tools, which are barrels, oval form, lens form, and taper barrel tool path, or the taper form tool path tools that we have. We're going to talk about the circle end mills or the barrel tools in our next section. But right now, you can see that we support almost any given shape of the tool. For the sake of simulation, you could even derive and make your own shape by revolving a sketch and using that particular shape as your tool for the sake of simulation. Not the sake of calculation, but for the sake of simulation, you could revolve a shape and use it. Right, let's go back again into the software. Let's discard. I'm going to open a very simple part. Okay, so, and here we are going to look at just purely 3 tool paths very quickly. The first one I would like to look at is machining the inside walls, which is pretty straightforward. So what I will do is I'll add from a template. Even here I've selected and kept a lot of templates. Let's see, that's the middle pocket. and I'll save the template. So what I'm using here is called a strategy that's called as MultiAxis constant step over, which generates constant step over irrespective of how the surface is. Not by looking from one particular direction, but it generates a constant step over looking normal to the surface at every given point. So in the geometry, I need to pick surfaces. So I'll pick my surface. So I'll pick this one, this one, this one, this one, and this one. These are the 5 surfaces that I picked. Now notice that these surfaces have cutouts in between. Okay, so I'll also show you how we handle these cutouts very easily. And I'm going to use parallel to curve. So I'm going to use that curve at the bottom. Yep, that's the curve I'll use. And the tool I'm using here is a 10 diameter ball nose. And in the tool axis control, I have defined a tilt of 80 degrees. That means it's going to tilt 10 degrees away from the surface. It's needed because I don't want it to touch the entire flute onto the tool. That also could be a method of doing, but that's a different method of doing. I'm going to give a tilt of 10 degrees basically to the vertical. So I've defined 80 degrees to the horizontal. And in my geometry here, in the surface, I have asked the software to fill the holes. So if there are holes within the surface, they will be filled up and it will be machined. Okay, so let's save this toolpath. Oh, check surface is not defined. So let's go to the gouge check. And in the gouge check, I have asked only one group to be checked. And that group is going to be basically the fillets at the bottom, because I don't want the tool to push into these fillets and to the surface. They have to be checked. And the reaction here with this kind of with these surfaces is to retract the tool up along the tool axis. Okay, very important word, along the tool axis till no collisions are found. Perfect. So let's save it. Okay, let's say automatic, and let's hit the calculate. Most of the calculations inside SolidCAM in 5-axis are not pretty lengthy calculations unless we used a specific calculation routine. Most of them vary anywhere between 15 seconds to 35 to 40 seconds of calculation time. So they're pretty quick. So if you look at the toolpath, okay, so we have a problem now. You can see that the toolpath has been done very funnily. That's because of my tool axis control. Instead of plus 80, because now it's coming down from the bottom side, it could, because I've just defined surface, it can approach from any side since it's 5-axis. So I'll say minus 80, I'll hit the calculation. Again, like I said, most of the calculations inside SolidCAM are not more than 15 to 40 seconds. Okay, so we've done a pretty neat calculation. You can look at the toolpath, very clean. And most important, you can see that it covered the surfaces. It covered the holes that were there in the surface and just bypassed them, moved over them as if there was a surface over them. If I look at the simulation now here, simple insight within the software. Let's run the simulation. Yeah. And if I look now at the machine simulation, if I take it to the machine simulation, okay, I've loaded it on a Mazak. And that's my part with the fixture on the table. And if I switch on the toolpath, that's the toolpath. Start. That's how it will machine it. Okay, so it's pretty clean, pretty fast generation, and most important, the toolpath quality is extremely high. Okay, fair enough. This was one toolpath. Let's also now generate the toolpath for one of the side surfaces and look how it machines. So I'll again add from the template the sidewall finish. Okay, I'll select the faces a bit later. Once I add the template, let me move to my surfaces, and I'll pick my surface here, and the drive curve is there. That's the drive curve. Okay, this is done. The tool is, again, 10 diameter in this case. Tool axis control, won't use minus, it's going to be plus here. Well, that's it. And in the gout check, I'm going to enable only with the tool shaft and the cutting portion. It needs to check for these surfaces that I just picked. And the strategy here I'm going to use is Retract Tool along tool axis. Perfect. Let's hit the calculation. Like I said again, calculation time isn't too much. Oh, sorry, this was not what I intended. I'm very sorry. I wanted to show you the generic one. My bad. So what I will do here is I'll add a generic 5-axis. So I'm not going to add any multi-axis constant step over. And here I'm going to say parallel to curve. Let's pick the drive surface. Pick these 3 drive surfaces. Okay, remember again, these are having gaps or holes in between. So I'll pick this curve. Okay, that's done. The tool I'll pick is tool number 4. Okay, it's tool number 4. Right, in the tool path, 1 millimeter, and it's going to be zigzag. Tool axis control, it's relative, so I'll say 75 degrees relative to the cutting direction. And in the link, I'm going to keep them as they are because I'll not do anything in that. But let's come to the links a bit in a moment. Okay, the calculation is done. You can see there are so many red patches. Okay, that's pretty much expected because it found holes and it doesn't know what to do with the holes. Because when I go into my links, the holes are simply meant to be retracted to the clearance plane. So if it says if there's a gap more than 20% of the size of the diameter of the tool, it should retract to the clearance plane. I don't want to do that. I just want to apply a blend spline. Okay, don't go to the clearance plane, but just blend between the 2 positions. Let's hit the calculate button. Done. And you can see that I fixed that area. Right. Now we have a problem here of retracts going too much at the end. That's because, again, into my links, if I go into my links, you see that when it is connecting 2 slices, anything more than 110% of the side step, it will take it to the clearance plane. I don't want that. I just want this to either change or I will just change the value to 500. And the ones that are being directly connected, just straight connections, I would like to change them to spline so that there are very smooth connections when it happens on the slices. Okay, so that's also fixed. You can see how easy it is to fix issues once you see them in SolidCAM. Okay, so we fixed the issue of the gaps that were there here. We fixed also the issue of these sharp corners, sharp motions. I made now generated into a smooth motion. Okay, so we machined this particular face. Now we have to machine the fillet. That also is pretty simple. Now to do that, I'll have to use a different kind of a technique. And this is a technique where we use the functions of SolidWorks. So I'm going to make a plane here because I just want to make a sketch. Okay. Okay, that's good enough for you. And 200 is good enough. And we'll make a sketch here. Let's go to the top view. And I will simply make 2 lines. 1 line here. Okay. And 1 more line here. Now to make the line exactly the same, I'll drop another construction line here. This is only going to be used for construction, and I'll trim off the excess. And I'll apply a fillet here between this one, 10 millimeters. It's good enough. So I've got a curve. This curve should be good enough for me. So I generated or made a sketch of a simple curve. Now I'm going to add simultaneous 5-axis again into the generic. Let's go to the geometry. I'll pick the geometry. These are the fillets that I need to machine. And okay, it's morphed between two curves. Let's go to the start. That's my first curve. And my next curve is here. Oops, that's not how much it needs to go. Yeah, that's all. So I have two curves, start and end, and I'm going to use a taper ball nose in this case because I would like to machine it. Do I have anything? Yeah, I have a 12 tip radius 3. Select that, and tool path, let's say it's 0.3 millimeter. That's a step over. In the tool axis control, now I'm going to use a different tool axis control. Like I said, we have got tons of methods. So we will say tilted through curve, and the curve that we going to pick is the one that I just defined using the sketch. This one here. Okay, so I picked this curve. That's the curve that I'm going to ask my software to follow whenever it's cutting the surface below. Okay, perfect. So we have almost done that. Let's save and hit the calculate button. Again, this is going to be a pretty quick calculation. Okay, calculation done. We have got a lot of retracts. We don't need that. So let's edit this toolpath, go to the links. Of course, we can always fix it, but I just want to show you that you can always go back, change this value. We can always would have set this value straight away in the toolpath itself. Okay, that's done. So if I now run the simulation of this, I'm machining only the fillets. You can look, it's clearing that surface, machining the fillet, and the tool axis is always passing through this particular curve that we selected. Okay, so we used a tool axis, a tool curve function. The curve was selected, and the tool axis always is now passing only through that curve. So, like I said, in SolidCAM in the generic, you have got tons of methods in which we can use to machine a part the way we want it, not the way the software is going to give us, but the way we want it to machine. Right, so let's pick another part. Okay, I'm going to take another part and show you the generic 5-axis machining functionality. And this time it's going to be a turbine blade. I've got a pretty, it's not a simple turbine blade, by the way. It's a complex turbine blade. We've got features on either side, fillets on either side, and surfaces on either side. We would not like to see the roughing because in most of the times the turbine blade roughing is done using 3+2. That's a simple 3-axis roughing, the positioning in the other 2 axes. We would like to see the finishing. Okay, so again here I have got templates. So I'm going to add operation from a template, and I've got turbine blade, main finishing toolpath. I'll apply it. It's purely parameters, nothing else. The geometry I'll have to select. Now what I've done here is, just for the sake of clarity, I've untrimmed this face. I'm just going to use this face to define the pattern, nothing else. Okay, my drive surface is going to be these surfaces. I'm not going to select the fillets. The fillets will be machined separately along with the wall. Okay, so these are my drive surfaces. That's done. My start edge, that's why I brought the surface out from the hidden side. So this is my start surface, and this is my end surface. Okay, the pattern is now going to be between these 2 surfaces. Okay, the tool here I'm using is a taper ball nose. Okay, many people would immediately jump on this and say, oh, no, for turbine blades you must use bull nose. I'm going to come to bull nose also, but I would like to show you the power of SolidCAM in which it can just switch over between tools and give you an excellent toolpath straight away. Okay, so in the toolpath parameters, everything is done. Only thing now, the function of that face is over. I'm going to switch it off, and let's go to the gouge check. And here I'm going to enable the check surface. Basically, the check surfaces are these surfaces where I would like the tool and the holder also to tilt if they get too close or if they get precariously close to these surfaces. Okay, this is done. And the second curve check that I've put is for the drive surface, wherein I've said retract the tool along the tool axis if you find any collision with the drive surface. With the first group surface, I said tilt, second retract. Okay, that's all is needed. And let's hit the calculate button. Again, it's not going to take more than 30 to 40 seconds to calculate this. Remember, this is a time-tested template, so you can use it for any kind of turbine blade that you have. Just take a template, apply it, and your calculations will be done. Like I said, any tool path, not more than 30, 40 seconds. Okay, that's the tool path here. Pretty clean. Look at the tool path. It's a pretty clean tool path that you have in SolidCAM. Okay, let's look how this looks on the machine. So here I have a DMG DMU 100 monoblock, and this monoblock machine is different. This has got a head motion, and it also has a table motion, but the table is mounted horizontally, but not vertically. Okay, so this is the part with mounted on the table with the with the tool, everything, and we can start the cutting motion. Smooth motions without any collisions. Okay, so it will just keep rolling around and keep machining it like it has to with a turbine function. Okay, right, so it will keep rolling on. There's no point in looking at the simulation till at the end, because honestly, I find it boring after some time. What we need to check is only the first and the last motions. Once they are okay, everything else in between is fine. Like I said, some people would have jumped up and said, nobody uses ball nose for finishing your part. How would you do it with a bull nose? Fair enough. So let's again bring a template. I've saved a template with a bull nose. I'll apply that. And again, I can reuse the geometry, but I don't want to do that. I'm going to define fresh new geometry here. My drive geometry is this. Like I said, please don't look at the fillets because we are not going to do the fillets now. Fillets will be the next step. So these are my drive surfaces again. And my start edge surface is that one. And my end edge surface here is this one here. Okay, again, this work is over. I'll say bye-bye to him. And in the gout check, we will use again the check surface, which is basically 1, 2, 3. I also would like to pick all these surfaces because these surfaces are going to be precariously close to my holder, not to my tool, but to my holder and the surface here. Okay, done. Now, the only thing I've changed in the tool axis control, the other one was always normal, looking normal to the surface. But here I have applied a lag angle of 30 degrees to this particular operation. I'll tell you why I have applied a lag angle, okay? And this is very important when you're using a bullnose tool. So let me save this. And let's calculate this tool path. Somebody is asking me if we have to make each machine in 3D before creating the program. No, these machines are supplied to you as part of the software. When you order the software, you have to tell us which machines you have. We build those machines for you, and it's only done once. Okay, when you call the post processor, the machine comes along with the post processor, so you don't need to keep it. It's only done once when we install the software for the very first time on your computer, or when it's done on your or when you do the programming. Okay, it's just once, right? So we have done our calculation. Now with a bull nose, what was the tool I used here? I used a 16 with a corner radius 3. So I'm using an inserted kind of a cutter with bull nose 16R3. Let's run the simulation in machine, because I would like to explain to you what happens when I provide the lag angle of 30 degrees. Now, why people don't like to use ball nose tools for finishing, especially on turbine blades, is that most of the times the tip of the tool is in contact with the surface. And we know that when the tip is in contact, the RPM is close to 0, or even the other small portion is in contact, the RPM is very low there. So the quality of surface that comes is not very good with a ball nose tool. However, it's not the case with bull nose. Now, why I have given the lag angle, I'll explain to you when it comes onto the surface here. Okay, that's a bull nose. I'm going to stop it here. Okay, I'll stop it and I'll switch off the tool path, and let's look at the contact of the bull nose. You can see where the bull nose is making the contact. The contact is happening on the front of the tool. If I had not given the lag angle, the contact would have happened at the center of the tool. Again, not the right place to be using for a bull nose tool. Okay, especially if you're cutting in a concave kind of an area, you should never use the center portion of the tool. Okay, here we're using the front of the tool, always in contact, always in contact. Okay, whenever it is cutting, only the front of the tool is in contact with the part. Okay, the advantage here is that you get the full diameter contact area, you get the entire RPM. So you get a much better cutting, much better surface quality. You can cut much faster. Remember, with a taper ball nose, it's not possible to go with a bigger step over. With a bull nose, you can actually go with a bigger step over and yet generate a similar surface quality that you would have generated with a ball nose with a small small step over. Somebody is asking that lens tools are very good for such functions. Yes, we will come to the lens tools when I show you the circle end mills in approximately 5 minutes from now. Okay, this is about bull nose. It'll keep continuing and machining it. Let's now look and quickly generate for one of the sides, for one of the fillets, we will generate the program because the other side is very similar. So I'll again add the operation from the template, and this time I've got a turbine blade finish, fillet finish. I'll add it. Here, of course, we cannot use bull nose. We can at the most use a ball nose or a taper ball nose. So I'm using a taper ball nose with with diameter 16 and tip radius 3R. Geometry, of course, is going to be, because I'm going to take some portion of the tool path also onto this so that I don't get any mismatch between the bull nose generated tool path and this one. There has to be some kind of an overlap. So I'm going to pick the surfaces. Okay, that's done. And the edge curve, it's basically this one. Like that. Here. It's going to go parallel to the curve. Oops, no. That one here, yeah, okay, that's done. I don't need to do anything much, but I'll just go to gouge check, and I'm retracting the tool if it finds collision on the drive surface, also the check surface. What is my check surface? My check surface are these three surfaces because the fillet is in contact and it could come very close to the surface. Okay, let's save it and hit the calculate button. There's nothing else. I have saved. The most important part is the creating of proper templates. And by creating templates, you actually end up standardizing your toolpath generation. So a senior most person can put all his experience that he has generated over the last several years, generate effective templates, and the engineers below him only have to just apply the template and select the right geometry. Okay, the toolpath is done. Again, looks nice and cleaned. If you look at the simulation this time, what I've done, you can see here, I'm using a 4+1. I have locked my, if I show you the toolpath parameters, the tool axis, you can see it's the 4th axis. That means I'm going to have simultaneous 4th axis, 4 axis, and the 5th axis is locked at -30 degrees. So that's not going to change. So the 5th axis is locked. I'll just right click on this. Let's go into the simulation of the machine. Michael, you're asking whether templates can be made as a part of the standard installation. That's a good suggestion. It can be made. I can provide all the templates that I've generated over the last few years, and this could be a part of our installation. Thank you very much for the suggestion. Let's run the simulation. And you can see here what is happening. If I go into the front view, my head is locked at 30 degrees. So if I look at the side bar here and look at the B angle, you can see the B angle is set at -30. It's not changing from -30. The only thing that are moving are the X, Y, Z, and the A axis. Okay. By doing this, it's actually going to machine a portion of the top flat surface and also the fillets. I've got templates also to machine the left side of the fillet. I've got templates to machine also the face of the turbine blade. Okay, so I have created these templates over last, in fact, the turbine templates I just created over last 1 week. I would not call it several years, but I did apply it to at least 3 or 4 different type of geometries, and they work very well. Okay, it might need a little bit of tinkering here and there, especially when you go on real complex geometries, but otherwise they work perfectly fine. Okay, that's about turbine. So we could see that moved from a simple geometry into turbine, which is a complex geometry. We'll move to even a much more complex geometry. When I look at the generic 5-axis, in fact, for me, the most complex part is going to be this, because honestly, nothing is visible. Everything is hidden inside. So we have what we call as a closed impeller. We are going to machine the closed impeller. I already have done it because for people who would like to know how this part was actually done from scratch, right from importing the part into the software till the end, please go to our webinar section on solidcam.com. Hopefully you should be registered there to look at this webinar, and there you have a webinar almost of 2 hours only for this part, where I have taken this part, imported it via Parasolid inside. I have done all the geometry necessary for creating the toolpath, including the tilt axis, tilt curves, and generated the geometries for machining it. And then I have applied some templates that I had stored again and machined this entire part in front of the users. And this is like 2 hours, and we cannot spend 2 hours here. So I have already done some machining. I'm just going to open. For example, what I did was I first of all made one portion visible. So I have given a different color to those surface because I want to know that I'm going to work on that. And I created offset surfaces and created 2 different groups. One group I said is the upper surface. I just created an offset or copy of the surface and trimmed only some portion and kept only that. So this portion we are going to machine from one side, and the other side, which basically overlaps sufficiently, I call it as the lower side. You can see that it overlaps almost 10-15 millimeters into the upper surface. So I created this surface, and these I called as the lower surfaces, and I'm going to machine it in a different direction. And then I have created another toolpath which basically overlaps between these 2 toolpaths, one coming from the top, one coming from the side. It just overlaps to make sure that there are no mismatch marks between these 2 toolpaths. So this is all I've done with this particular part. But like I said, this entire exercise of creating this is approximately 2 hours. So I can't spend 2 hours today because we have to cover a lot of things. So what I have here is the upper surface, sorry. And if I go into my first toolpath here, I'll quickly show you what is the items that I've selected. It's morph between two boundary curves. And these are the surfaces that I've selected as a part of my machining surfaces. And my upper curve, that's my start curve for pattern generation, my lower curve for pattern generation, and then I have got the tool axis control, which is basically a tilt curve. Now, these tilt curves were created using some functions. Why they have been created like this is available in my webinar that I did a few weeks ago. So this is the tool curve that I've used to control the tool axis. Right, and some gulp check faces that I selected. Let's hit the calculate button. Again, like I said, it should not take more than 25-30 seconds to calculate. Can this part be cut from a solid block? Of course, you can see the first, I would say the first 5 toolpaths are basically 3+2 roughing toolpaths that I've done to open the pocket in simple 3-axis, but +2. And then I've done a 3-axis undercut finish because some areas are still undercut. I don't want to do 5-axis there because they're too small areas, too small an area to do 5-axis. Apart from that, everything else is only applying the final collision checks. And like I said, not more than 30 to 40 seconds, we have the toolpath. Perfect. So we have a very nice toolpath in the area. Let's run the simulation in machine. This time I have a DMG 65 monoblock. This part is quite big. It's approximately 300 plus in diameter. Okay, so this is the part and the toolpath. Toolpath is not visible. I can get the toolpath visible in the visibility, but I don't want to do that. And let's start. That's how it will start machining. Let's increase the speed. I've used a lollipop tool to cut this part. And this will just keep circling, 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 spiraling, spiraling, spiraling till it reaches the end of the surface. Okay, so this is how the motions of the table are also going to be. Okay, so this is how you could also use generic 5-axis to do parts like these. Again, I have got templates. Michael, thank you very much for this suggestion. We're going to make this a part of our software. Okay, so the next one I did was to switch off this surface and switch on my lower surfaces, and we'll calculate the second toolpath here. Again, I'm using a lollipop tool. Again, here it should not take more than 30 to 45 seconds to calculate. Most of the calculations here are done live, okay? I've not saved anything in this. The only thing why I wanted to do this in this way is the amount of time that is needed, because otherwise this part can easily take 2 hours. You can see the webinar that I've done. It's done live, start to end. It's for this particular part, importing it till the final finishing. Somebody's asking if you can send me the recording of the webinar. Yes, of course, recording is possible. It can only arrive. It can only arrive to your inbox within 24 hours because we have to process it, put it on YouTube, and then as a part of our email to everybody who has attended the webinar, this particular link goes, the recording link goes to the users. Okay, this also has been calculated. What I will do is I'll also calculate the overlap toolpath. This should not be more than 5 to 10 seconds. Okay, that was approximately the same. Select both of them, and I'll take it to the machine simulation. Okay, taken the part, the tool path, the tools, the fixture, everything, loaded the machine, and we are here. So we are machining now from the side, from the small area, and that's how it's going to machine. For many of our competitive systems, most of the things cannot be really done in generic. Either they're not aware or it's too complex for them to do generic 5-axis functions. So they have developed application-based functions, which are, first of all, very expensive to use. Of course, they do a lot of your work easier, but then you don't have one system doing everything. You have got bits and pieces of system doing different areas of different parts. So here at SolidCAM, I can actually use a generic function and machine any part I like, the way I want. Okay, so this is how it's going to machine. Now let's look at the overlap, because it's very interesting. Because in the overlap, since it's doing the machining quite inside, you will see that the holder is also entering into the part. Now, the auto tilt function, the auto gouge check tilting function, is so powerful that it can even take into account your holder and make sure that your holder is not colliding when it's doing the machining, when the holder itself is inside the geometry. Now it's actually doing the fillet, the merging fillets between those two areas. So it's quite a steep fillet that we have, and that's how it machines the fillet. So no collisions, nothing. Straight away, the tool path comes up. Again, this was a part of our template. Right, so generic, we are coming to the end of the generic functions. Like I said, you can use generic to machine any kind of part in any way you want it, whether it is turbine, simple blade, simple parts, or even a part as complex as the closed impeller. Right, let's jump to our next area, and that's another 10 minutes. And here I'm going to talk about the circle end mill support. The circle end mills are basically the new generation tools that have been released by several tool manufacturers in the world. Okay, now inside SolidCAM we support the 4 major shapes. The 5th one is coming. The first one is a barrel shape, where you have got a very large radius on the side, on the flank, and the bottom is flat. And then you have an oval form, which has got basically 2 radiuses, one large radius and one tip radius. And then we have a taper form, where you have got, again, a very large radius, but it's not tangent to the shaft. You need another 3rd radius to make it tangent. And then you have a lens shape, which basically has got a very large radius at the bottom. So you have got these 4 shapes that are currently supported inside SolidCAM. So now more and more tool manufacturers are introducing these new product lines called barrel profiles. And they promise up to 90% reduction in machining time when using these tools when compared to a regular ball nose end mill. We introduced this support more than 1.5 years back inside SolidCAM. And like I said, we support 4 different shapes. The advantage of going with the circle end mills is that with a very large step over, because of the very large radius, we can achieve a scallop much smaller than what we would achieve with a ball nose tool with a very small step over. Clear-cut example is on a straight wall, where you could have an AP or depth of cut of 0.5 and generate an RA of 1.22, whereas with a circle end mill, the same RA or even less than that can be generated by 3 times the step over. That is because of that large radius that exists on the flank of the tool. Thereby, you actually end up reducing your machining time. There are other reasons, compelling reasons, why you use the circle end mills, and one of them is basically deflections. If you have deep paths, and if you're using let's say a flattened mill can start deflecting if the L/D ratio goes beyond a certain value. And instead of getting a straight flat surface, you will end up getting cusps on those surface. Whereas with a barrel mill, because it has a radius on the side, even if it deflects, it will always be deflecting on that large radius. So it doesn't affect the scallop. So it becomes a much more robust cutting in cases where you have these deflections. Okay, so the benefits are, first of all, you get very low cusp heights, you can balance machine inaccuracies, and there is a smooth transition between cuts because of that large radius, and low dynamic disturbances due to short tools. Most of the circle end mills are not long. You'll see that, for example, a 16 millimeter circle end mill or a 12 millimeter circle end mill won't be, the entire length of the tool won't be beyond 70 to 80 millimeters. Okay, so out of holder is less. And I'll tell you why we need so less and how we can work with such a less OHL of the tool. The circle end mills can also, the other reason is machining deep parts when you have got straight walls. I'll show you an example. You can tilt the tool, but you cannot tilt a flattened mill. But you can, of course, tilt a ball nose. But if you tilt a ball nose, you're actually going to need a very small step over to machine the entire part. Again, a waste of time. And this barrel tool offers a great advantage there. We can have pretty large step overs and generate and machine the same part with much less time. The oval form, like I said, has got two tip radiuses, the large and small. You can use a small radius like the taper ball nose and go into areas where the corners have very small radiuses. So it can have a dual purpose. There are some, like I said, barrel tools or circle end mills cannot be used everywhere. They are not a solution for every geometry. For example, if you have a convex shaped geometry, it makes sense to use a flattened mill than a barrel tool or an oval form, because you're anyway going to never achieve the shape of that convex by giving a large step over. Okay, you anyway have to give a small step over. So in such cases, barrel tools don't offer you any significant advantage. The other areas where you cannot use barrel tools is that when the area itself is so small that the barrel tool cannot enter. Okay, large radius cannot get in. In this case, again, the barrel tool does not offer you any significant advantage. In fact, they cannot machine at all. Another very important area where barrel tools cannot be used is if your machine itself is 3-axis, because barrel tools are effective only when you can tilt. And if you cannot tilt your spindle, you cannot tilt the tool, you effectively cannot use the benefits that they offer. So basically, these tools are a big no-no on a 3-axis machine. Another area where it's a challenge basically with the barrel tool is that when your surface itself has too many variations inside it. If it's not a single free-flowing surface, if it has some different shapes in between, then the challenge comes up on how we are going to program then, because we are going to need two different programs. One machining the large surface with a bigger step over, the other one machining the inside one, which is not the same shape, with a smaller step over. Barrel tools, if you look at the catalogs of all the tool manufacturers, they say very clearly that these tools can be used only for finishing. They cannot be used for roughing. They cannot be really used for semi-finishing. And at the most, material they can remove is between 0.2 to 0.3 millimeters, or at the most, they can go to 0.5. So it's very important that you machine your priority of machining of the surfaces is very right. You can't directly go and machine the fillets first without finishing the flank, because then your fillet area, the weakest point on the barrel tool, the bottom area, is going to get a lot of load, and that's going to wear out very quickly. Okay, so you have to be very, very particular on which area to machine first, which area to machine next, especially with barrel tools. SolidCAM offers a completely different solution for tilting. We can define which point of the tool will be in contact with the surface. This point can be defined by a percentage, or it could be defined as a distance from the tip, or it could be defined as a percentage distributed over the barrel profile. And the point can be a static point. It can be the same point throughout, or it could be dynamic. You can start at 50% and you can go up to 15% of the barrel profile, and the tilting will automatically adjust accordingly. Right, let's look simply quickly at a part with the barrel tool. Somebody asked me if SolidCAM can help you in selecting the right tool. Well, you select a tool and it'll tell you what result you're going to get with that. Sorry. Okay, so I have this tool, I have the part here, and I have a surface which is having a very large radius. It's obvious that if I use a ball nose, I would need a very fine step over to machine the surface. If I use an end mill, I would not machine the surface beyond a certain length. Okay. After that, your holder comes into play, and that's it. That's the end of toolpath generation. So what I've done here is I have created a tool, which is a oval form tool, and this diameter is 16 with a tip radius of 3, and the profile radius here, the large radius, is 75. So if I go into my tool definition, you've got barrel shape, oval form, lens form, and taper form. Okay, so we have I've selected the oval form with diameter 16, tip radius 3, and the large radius 75. And in the tool axis control, what I've said is that my first point of contact should be at 60% of the barrel profile, and my last point of contact should be at 20% of the barrel profile. I have not defined any angle here. The angle is going to be defined, or angle is going to be generated by this contact points on the barrel profile. Okay. So let's look at the simulation, but it's not possible that my entire 20%, it would come exactly at 20%. It can stop, because at 20%, it would actually create collisions with these two surfaces. And I've put these collision as a collision check. I've put this as a collision check. I've put the bottom two surfaces as collision check. Right? So it might not go all the way up to 20%. It can stop at 28% because of the collision check. So let's look at the simulation on how the toolpath looks like. By the way, this toolpath generation did not take me more than 10-15 seconds. I could have generated, but let's do it quickly. So where is my first contact point? So I'll take my tool. It's entering into the geometry, and once it has made a contact with the surface, let's zoom in, and you can see that my first contact point is at 60% of the barrel profile. Okay, I did not define what should be my tilt angle. My first point is here, and as the tool moves over this particular surface, it will keep changing the contact point. So let's reduce the speed and play. You can see that it's now changing the contact point, and as the contact point is changing, it's also changing its tilt. That's why we can use really short tools in barrel, in the oval form kind of a profile, and sorry. That's why you can use really a short tool, and you can actually really go and machine pretty deep areas if the surface allows you. Okay. So this is how it's actually going to distribute itself over the entire profile. So if you look at the toolpath, goes right way up to here. So here it will not be exactly 20%. It might be probably 28% because it stopped, because it was going to generate a collision with the surface. Okay. Let's see that. Let's run the simulation again. So we support all the 4 tools. Our 5th tool support, you can see as it goes down, the contact is changing, so is my angle, tilt angle. I have not defined any angle here, but And once it goes to the end, you'll see that it's not actually, it stopped here. So it's not 20%, it probably could be 25% or 28%. Because it would have created a collision with the fillet here, it stopped and retracts up beyond what is allowed, okay? So you can use these tools, reduce your machining time, machine almost any kind of geometry, apart from the ones that I just said, they are big challenges for us. Okay, so let's move ahead from our generic. Let's move into the application-based strategies, which is be pretty quick because not much to see out there. The first one is screw machining, or what we call as rotary machining. It's a very quick generation of toolpath, which generates 4-axis rotary roughing and finishing toolpaths on arbitrary meshes. The input probably can be a solid model, or it could be a surface geometry itself, or a mesh geometry. And we support ball mills, end mills, and bullnose. Manufacture of oil fields. The parts generally are used in oil fields, automotive components, or crankshafts, and also plastic machinery parts like extruder screws. You can give any kind of geometry that can be fit on a 4-axis machine, and it will generate roughing, arbitrary roughing, and finishing toolpaths. Let's look quickly at the part. Sorry. Let's open. So the roughing of screw machining basically is that the roughing of screw machining is basically a simple 3-axis kind of roughing, but it is done in 4-axis space or cylindrical space. So what I have here, I have the part, which is basically the entire 3D geometry. I would like to keep an offset of 1 millimeter stock for finishing. I'm using a 16 corner radius to bullnose for roughing. And in the toolpath parameters, depth of cut 2 millimeters, side step 6 millimeters. Cut tolerance, since I'm going 1 millimeter offset, I can safely go up to 0.15. That's all that is needed. And in the tool axis control, I just need to define which is my 4th axis of rotation. Once this is done, I simply hit the calculate button, and these calculations are pretty fast. They don't take much time. If I had to do this particular roughing in general, probably I would have taken a little more time. That's where the application-based strategies come quite handy. They allow you to define bare minimum input, but yet give you an excellent toolpath at the end. But again, the application-based strategy is very limited. Okay, not every part can be put into an application based strategy. For example, if I have a screw machining strategy, I cannot take an impeller input and ask it to calculate. It will not do it, okay? Because it is expecting a different kind of a geometry. Similarly, inside an impeller, I cannot take a screw and put it and ask it to machine. It will not, okay? So these are the limitations. So that's the first roughing. I simply selected the part, I selected the tool, depth of cut, side step, and my roughing was done. In finishing, I'm using, again, the generic 5-axis, which is the multi-axis constant step over. And I've selected the faces to finish. So if I look at the faces here, these are the faces that I would like to finish. Simple. And let's calculate. I'm just going to calculate only one of them and show very quickly how we do it, because everything else is similar. Somebody asked a very valid point, and I believe this was never asked me before, and I really have to check this. This could be checked from 2 different sources, the tooling manufacturers themselves, as well as our software developers. So the question is that we do not maintain, or rather we maintain a constant VC when we are going on that surface with a different contact point. Very valid question. It's like turning, okay? It's like turning where you have got a constant surface speed, so the RPM varies. When you start from a bigger diameter and go to the tip, the RPM varies. Similarly, you should have a different RPM for every cut that you take, because your contact point here is varying, so is the diameter. But what I have seen specifically in the catalog of EMUG is that they ask you to use a particular contact diameter, and they generate the parameters for that particular contact diameter. You could call it as a mean diameter, which is between the lowest and the biggest, and they ask you to use the parameters for that particular diameter. So this question, I have to put it to the tooling manufacturers as well as the software developers to see what we can do. But at the moment, it's going to be constant VC throughout. Okay, so this is how we also generate our finishing toolpaths. Okay, very simple, very nice, clean toolpath that we get here. And we also can finish the floor also using the same functionality. Going to be very fast because there's not much. Here I'm using a bullnose to finish the floors. And since I have got toolpaths coming from this side, that is this surface is one, and this surface is another one, I have got a region here which is not machined, okay, because it's going and stopping because I'm using a pretty large cutter. So for that, I have created another toolpath here by defining this different kind of a geometry. We call it as an overlap toolpath, which overlaps between both of these toolpaths here. And here it's using a smaller tool to make sure that it finishes that radius also. So this region I've done using this kind of a toolpath. Again, this is coming from the generic toolpath functionality. Right, so that's about screw very quickly. Let's move ahead to the next one. Sorry. We are now entering the most important aspect of our application-based, and that's the impeller or blisk machining strategies. Okay, I'm going to quickly run through the impeller machining. Let's open a part. Not a simple part, but a pretty complex part. Multi-blade. Take the impeller. So I have a nice impeller here with pretty thin blades and very less area to work with. And in impeller machining of SolidCAM, if I edit this toolpath, you see that we have got roughing, we have got blade finishing, we have got hub finishing, and we have got the fillet finishing strategies. So the first one that we are going to use is the roughing. So what I have here is in the geometry, I've got not the new, but I would like to show what has been picked. So I'll go here, show. So what I've done here is I've picked a group of 2 main blades and 1 splitter blade, including the fillets. Very important, fillets are also be included as a part of the blade geometry. So 2 main blades and 1 splitter blade is selected. And I've also selected 1 piece of the bottom surface as my hub. Okay, you don't have to select everything, it's not needed. SolidCAM just expects 1 small piece so that it knows exactly how the hub is. Internally, it will do its own calculation of the surface. Okay, and what else? I have done 2 roughings here, one with a short tool with a diameter 10, because it can really rip the material even at a depth of cut of 10 millimeters, and it can machine the part. So it's a diameter 10 with a corner radius 2, taper ball nose. And here in the distance, that's the depth of cut, 10 millimeters, and the side step is only 0.8. And I'm going to go, you can see that there's nothing, most of the things are automatic or they have been set default by the system. Okay, all you need to do now is simply hit the calculate button. Okay, that's done in under 10 seconds. It calculates. Because I've just said do 1 blade, it has done only 1 blade, and it has gone up to here because that's up to where the tool can reach. Beyond that, if I go, it's actually going to create a collision between the holder and the tool. So the tool path is stopped out there. Okay, so that's how my roughing looks like. So if I run the simulation and Solid Verify, probably will run the calculation of the previous operations. Okay, that was my first stock, and that's the zero clamping fixture that I've used to clamp the part, and I can stop the machining. Let's switch off the holder for a moment, and that's how it will cut. $10mm at every depth. Okay, so it'll keep opening 10mm, 10mm, and 10mm. I can actually show you a photograph of how the part looks like on the machine when this roughing has been done. So as it reaches the splitter, you can see that now it isolates into two regions. One is the left region and the right region. So it roughs out the left region, then goes again into the main region, into the right region basically, and starts cutting. The tool that I had got a small relief on the shank, so that particular message is irrelevant. That's basically the shank touching the stock. Okay, so that's how it's going to cut. And for people who are more interested in how it looks like, I'll just show this. Of course, this is a different impeller. This is not the same impeller. On the left side is the roughed out impeller, and on the right side is the complete finished impeller on the machine. Of course, this was a different impeller. This is diameter is approximately 450. The one that I'm showing you is approximately 250 diameter. Okay, but the tool used was the same. Okay, so that's how it cuts with 10mm depth of cut, and then the next one is done with a different tool. Okay, so like I said, I can edit this part. Since I have done only one, I can go into my transformation and I say machine all of these blades. Somebody's asking if we can use plunge milling strategy to machine it faster. Yes, of course, you can do that. In fact, I would suggest that you go not with 5-axis roughing, but with just plain 3+2, the automatic 3+2 functionality, and it will do it even more faster. Or you could use the eye machining functionality in 3+2, and it will do the machining even faster, because anyway we are cutting aluminum in this, so it's going to be even more faster. Right, so that's how it generates the toolpath for all the other 7 segments. Whatever remains now will be done using a 12 diameter taper ball nose. This is a lengthier tool. It's a slender tool, so here I cannot go with a bigger depth of cut. I'll go with a smaller depth of cut, but not 1 millimeter. It's going to be about 2-3 millimeters, and the remaining areas are going to be machined using this particular tool. Okay, so this region is now roughed out. Perfect. Now what remains is basically semi-finishing or finishing the blades. They are both the same. So I've got the blade finishing function here. I just have to select one set of blade. So if I go into the geometry here, if I show you the geometry, I just select one set of the blade, including the fillets. Let's calculate. And what I have here is the tool axis control. Everything is automatic. And the parameters, I'm using 1 millimeter step down, machining full. Because this particular impeller also has a radius towards the trailing edge side, I cannot stop it here. I'll have to roll my tool around this fillet here. Okay, so let's hit the calculate button. Somebody's asking what kind of parameters to be taken into account when you're machining such parts. First of all, you have to really listen to your tooling people. Okay, they know much better when they are handling such parts. So the RPM, feed rates, depth of cut, and side step need to be taken. And please use specialist people who know what impellers are, and not somebody who just sells solid carbide end mills. No, this is a specialized function, and it needs special care, special support. So use the help of those people who know these functions very well. Okay, so take those parameters. The most important thing here are the parameters. Toolpaths anyway are taken care by SolidCAM. Okay, so finishing is done. It's simply running like a spiral, starting from the edge, from the start, and going all the way down. So if I run the simulation, the finishing can be done in two ways. The finishing can be done, so please. The finishing can be done using multiple cuts, or you could do a swarfing of this function with a single pass. But majority of the cases, the impeller surfaces are not classic or ideal for doing swarfing. Okay, I'll have to shut this. Sorry. Let's. Thought that it will stop, but it didn't. It's continuing. It's going to take a long time if it does that. Okay, let's reload the part. Okay, again, some people have asked a very valid question on impellers, I think, because they have got this experience of buckling of the blades after, especially after you've done the finishing. When you remove the part, put it on the faceplate and allow it to age for, let's say, a day, and then you take it to the CMM, it shows a completely different picture of the blade. The blades would have buckled. Sir, the most important thing here is going in stages. Okay, you don't machine right from top to end in one go. You will machine in stages, especially after roughing. When you have done, we generally recommend, some people don't do that, but we generally recommend aging of the part, because it's a really stressful process, the roughing, and it does induce a lot of stresses. So we, in some cases, some of my customers are doing it in stages. So they machine the top, then machine the bottom, and wait, allow it to age, put it back, and then do the finishing. Thereby, it reduces the stresses, and the reduction in stresses will reduce the buckling of the blades, basically. Now, the part that you saw here, this part, this did not have any buckling. This particular part, the upper thickness is about 1.6 millimeters, and it goes down, comes about 2.5 millimeters. That's the thickness that we have. And here also we did it in stages. We allowed it to age. In fact, we roughed it completely for one full day, and we put it in the night. We allowed it to age and came in the morning and then just finished the part. Many people won't agree, but there are other ways of doing it. Okay, so let's also calculate the splitter, which is basically the same functionality, or like the main blade. We have selected the splitter blades with the fillet. Yes, somebody is saying that the depth of cut causes buckling. Of course it does. That's why I said you need to get in touch with the experts, the tooling experts who precisely know these problems, and they will suggest you these particular parameters, which in fact, the parameters that we wanted to use for the impeller that I showed you was overruled by the tooling guys. They gave us completely different set of parameters. Okay, so you have to really use those parameters. I wouldn't say you will have no buckling or no warping at all. There is going to be warping, okay, but it's going to be bare minimum when you follow the process that has been suggested by the tooling people, especially the parameters. Okay, so that's the splitter. Now, if you look at the fillet it's not a constant fillet, it's a variable fillet. So I have to finish the fillets. Otherwise, this part is going to look really ugly. So we have got a function to actually finish the fillets. It's called as fillet finishing, where it provides some passes from the blade side, some passes from the hub side, and they merge together to finish the fillets. Again, here the geometry that I've used is the complete blade itself, including the fillets. Okay, so let's hit the calculate button. This will take another 20 seconds. So if there are questions, you can please keep them coming. Okay, so that's the fillet. It's going to move around the fillet and finish the fillets. Okay, I've given a large step over. You could give a smaller step over to machine the fillets. It will just keep spiraling around the entire fillet and just machine the fillets. Once that is done, we go down to our hub because we also have to finish the hub. Although I've seen that people really like to do some kind of a polishing kind of a finish on the hub. You don't need that kind. Yeah, rough finish is good enough for hub because that's not the main area. The main area is the blade itself. Okay, so we have got hub finishing here, and I've given a step over of 1 millimeter with the same tool that I used for finishing, 12 with a tip radius of 2. And let's hit the calculate button. Again, here it's going to be pretty quick. It doesn't take much time to calculate. That's the advantage with application-based strategies. Okay, hub is also done. How much stock to be kept for finishing? Well, it depends on the geometry. This particular part, we used to do it at the exhibition at IMTEX last year, and we almost did 1 impeller per day on all 7 days. So we had kept a stock of about 0.7 for finishing. And that was good enough for us to finish this. This was machined on a Herco VMX10i. It was a 5-axis machine, small machine, because the impeller itself was also small, just 250 diameter. Right, so that's about impeller. Quickly, I'll jump. I know we are close to 2 hours, but I just have 2 more items to show. I hope I'm not, it's pretty interesting. I'm not boring you guys. And the other one is a blisk. So I'd like to take a blisk. And in the blisk, I have already defined the process. I'm using a combination of generic 5-axis as well as multi-blade. So you can do a lot of things with SolidCAM. For example, I would like to rough the blisk. So I can rough the blisk even without using the multi-blade functionality. I will use a bullnose and I will just scoop the material out in 5-axis between these 2 blades. So I have got the blisk roughing, so I'll just calculate that. It's a generic 5-axis functionality. It's basically parallel to surface functionality where we have selected the entire blade without the fillet and the bottom surface, and that's it. That's all that is needed. Select tool, give the depth, give the side step, and we could come up with a very nice tool path for roughing. That's it. So we have roughed out using, you can see the tool that I've used. I'm using a 12 corner radius 2. It's a bullnose, and I'm going with the parallel to surface function. This is a generic functionality. This is not something application based. We don't have something like special function for machining blisk. No, you can just use simple application generic functions to machine anything the way you want. The only thing what we have done here is we have used a function called as area roughing to generate the roughing passes in between, and I've used simple bullnose to machine it. Of course, I can even rotate this entire toolpath. There are 34 of them, so let's run the calculation again. Okay, it's almost done. It's now providing the links to all those 34 areas that it is generated. Done. So it took, the calculation time is approximately 23 seconds. So that's the blisk roughing using simple generic functions. Also, you can use oval form tools to finish this. So what I've done here is again a generic 5-axis functionality. I have used the blisk using the morph between 2 curves functionality. I've used a 10 millimeters with a tip radius of 2R and the large radius of 85R. And in the tool axis control, I have said start at 50% and go down and touch up to 20% and stop exactly at these surfaces 1 millimeter above. Okay, so whatever area that remains, again, is the limitation of the tool itself. Some area will remain, it will be unmachined. That you can finish it using a taper ball nose or a ball nose tool. So let's run the calculation. Okay, that's done. Some people were asking whether why can't you use the plunging pattern, but the plunging pattern is out here. We've got the plunging pattern out here, and we can use the plunging pattern also. What I showed you as simple 5x roughing, we can use a plunging pattern here. Okay, so this is how my toolpath would have looked like if I've used the oval form tool. So I'll run the simulation. My first contact, you can see, is at 50% of the barrel profile. And my last contact will be somewhere here because it can't go all the way down, because otherwise it will create a collision between the bottom surface. And let's run the simulation here. It's nice spiral toolpath, continuously changing the contact point. Okay, so let's go here. And let's look at this contact point here. I'm going to switch off the toolpath. You can see that my contact point is somewhere here down. Okay, so if it comes here, yeah, my contact point has now changed. So it keeps changing the contact point. And once it comes 1 millimeter close to the bottom surface, it will stop the toolpath, trim it, and retract out. Whatever remains then can actually be used or done using the generic function or the blade finishing function. And here what I've done is I've selected the entire blade, but the area has been controlled here by defining the percentage. It starts from 85% and goes to 100%. That's it, simple. It's a no-brainer here. So you can actually make a combination between generic and the other machining. So that's how it is done. If I run the simulation, of course, I have not given any holder here. And that's how it will machine it. So the remaining area gets machined with the ball nose. Okay, right. Let's jump to the last two, basically. I'm going to go into what we call as a multi-axis roughing. And let's open a part, especially for arbitrary roughing in 5-axis. So I have a part like this. It's pretty large diameter. If I measure it, that's about 800 millimeter in diameter, and I have pockets on the side, and I would like to rough them out. Of course, I can use 3+2, but I have also a possibility to use 5-axis roughing. So what I have here is I have defined my floor. The floor surface needs to be defined. I need to define the wall surface, which can also include, by the way, the floor surface, but the software is pretty intelligent. It will isolate the floor area and only keep the wall area and machine only the wall area. And the method that I've used here is called as a contour. It's like simple 3-axis roughing for molds. Okay, outside to in, inside to out. That's the method that I've used. The tool here is a 16 corner radius. It's a bullnose, R2. In the toolpath parameters, my depth of cut is 3 millimeters. My step over is 10 millimeters, and tolerance is about 0.1. And we are using one-way machining by regions. You can see it looks very similar to 3-axis, but the output that it generates is going to be full 5-axis. So let's calculate this. Okay, this is done. Let's look at how this looks on the machine. Let's put the simulate, take it to the machine. And it works basically on updated stock. So the stock definition is a must. So it has to know where the stock is before it actually starts the calculation. Okay, so I have got the part, the tool, everything, and can start the simulation. You can see it's almost looks like a 3-axis, but the motions are in 5-axis. Right, it will go down until it reaches the end. Increase the speed, ramp, and then start level. It will ramp, go in, and then open the pocket axis, full 5-axis. Ramp, ramp, machine. Okay, this is one way of cutting it. Another way is to use what we call adaptive style, or a style where which ensures on the tool. And let's area this is suitable for it. We have rough out this area, but the here with the adapter is that I can use full root length of the tool to generate parts. So what I've done here is in the strategy of multi-axis roughing, I've used a function called adaptive. The tool is 16 and the toolpath power step millimeter and desired step 4.8. Because it's aluminium, I would like to do zigzag machining. So when it is doing climb, 100% of the power, but when it's doing conventional, it is up milling, will reduce the step over to 80%. Okay, that's it. Let's calculate this. Done. Calculations of, and you can see this is the adaptive strategy. Looks very similar by machining. So if I now take this input for simulation, it will look like. Webinar is actually being recorded. Get recording of your webinar on your email. Part of our messages that goes the webinar is over. They are automatically sent. Let's run the simulation, and you can see that it's now doing our round area. And once it hits the wall, it will only start reaching. That's how it will start doing. So this adaptive strategy that I might. So we have got the regular content file as well as the adaptive. Let's go to the last portion and get another application-based strategy. This time it's the positioning. Got a cube, a geometry. How the tube looks finally is something like this. Okay, so the tube looks something like that, and this. Now, thing happen both roughing as well as using the application-based machining strategies. Okay, so what inside the portioning? Again, this is an application-based machining strategy. We have got roughing, plunge. So we have can apply any of these functions. Let's for rough and the so let me show the faces selected as. All these interfaces selected as my machining face. Okay, right. So and the tool selected. It's a you can use a ball nose tool here or a lollipop. We have selected a lollipop tool here, diameter. Toolpath pass, my step is 5 millimeter, on is 3 millimeter, and I'd like to machine both sides, maximum from this side to go all the way up to wherever it can. The region machine, retract machine from the other. It's particularly by the saw. So let's save it and and you can it only started side and it goes all the way up to here to the maximum point possible, and remain it comes, retracts, and starts machining from this side. So if you look at the simulation, let's go to the solid verify sim. Let's set the region of interest. Start. It also to account, remember, has entered the tree. It's taking into account holder collisions inside the. It's gone all the way to extent as possible. Thing that is not possible retracts and it comes to the other side and starts machining the part. So you can see that it's roughed out the sides, the tube. The fit works on a simple. I selected the same here, and I'm going to use the spiral finishing with the same tool, so you can just hit the button. Asking if we can pre-drill in the tube. You can. Once you pre-drill, it will understand that the drill has happened. It will take the updated stock and it will not machine the area that is already. That's the. This is to run the finish. Let's run the simulation. And the host CAD it's into the other area. Let's start. You can set as much as possible. It's doing 3 axes, and the moment 3 axes is tilting, and it starts machining after it tilts. It takes the holder also into the area where is machined from the what is not possible. It machines from what is the bottom side. Done. So machining. Ports customers use for machining the ports. They're also machining tube aerospace. So pretty powerful function. The last portion of our webinar, and that's the drilling. So I'll open the part and we will part here, and it has got holes every side, every possible side. So I have to create drilling programs without having the need kind of or anything. I need to create programs this. So go into operations, multi drilling tool, and I'll drill. The total length itself is 60 out of fold, only 30 millimeters, and I'll define a holder to it so that we kind of collision. Okay, I've created that. That's how my drill looks like with and the tool. Okay, let's go into the geometry and I'll say new drilling geometry. In the drilling, I can this. Now, this could be you can ask for a through hole or a blind hole. You can ask to pick a certain diameter. Just find only diameter holes. It will only find diameter holes. Or I could say the whole line from 0 to minus 25. Any holes that have got this depth, please only pick those holes. Okay. Or I could pick the hole by color. I can say pick from more, say pick this green color. Okay. And then all that are having this sort of surface. So I can apply different filters here. So I would like to have a picture of all the holes. So I'll say find. So it quickly finds the holes for me in different directions. That's the direction we have here. So okay. So you can see also, oops, I'm here with one of the, see where this on that one, this one, this hole. Problematic giving me from right. So it is now isolated for me here. This is the hole. I'm going. Oh, I think this is a one. Yeah, this hole. So I remove this hole. I don't want this. This would create me. Other holes, I will select it. Okay. The tool is already selected. You can see it's automatic. Okay. Need to the depth of the hole also set automatic. Okay. You can edit. You can go into the depth edit and you can pick E and you can edit the depth of that group. I want to go with the entire as possible. In the technology, the first one is a sorting pick on its own. So I would just pick the whole. This looks like an electric kind of a thing, not how I want this. So I will go to the shortest possible distance and show me the sorting. Now this is much more human. It's much better to the. You can set into, so you can set the pattern. You can set this pattern. For example, if I set this pattern and say show sorted, it will show me how it has happened. Then I could go into a certain pattern. Patterns are available. You can select each pattern and it will show you the sort. I would like to use distance. And then I'm using hidden, it's asking me what is the drill cycle you would use. So I like to use drill cycle. It's nothing but the one cycle. Tool axis control, I would like to have access here. And without check, of course, I'm going to enable. And I like to check only the whole thing else because I don't want the holder to guide against the surface. So I will pick all these flat surfaces that are there. These flats there, my holder will come and stop. Okay, here. Yeah, that's it. Because also these, it's imperative that I pick these surfaces all the whole region. Okay, so I've selected this. So I'm sorry, and this. Okay, and the tool let me parameters before surface, and let's do that. Okay, done. Now use the automatic clearance plane to the point. Want that, edit the, and I'll say use sphere of diameter 250. The Z is 295. Let's see if the value holds true. 50 distance 10 mm each. Let's calculate. Yeah, it's use different kind of mechanism and simulation. Of course. And simulation is done. We will be in the webinar. If you have questions, either you can ask the questions here to us, or you can email them. I'll just, by the time that's happening, I'll just open the last slide or insert a slide in between. And I will put my email ID, info.india@solidcam.com. So you can use this email ID and write if you have questions. By the way, also download the software completely free of cost for 60 days. You can product. Once you have, please let us know what machines you have so that we provide you processes, including machines, so that evaluation can be very nicely. We can also provide you with an online training of the product, and you can evaluate the product and work with the product as if you're working. Okay, that's the level of support we give. Okay, let's run a simulation for the full few holes and does. So it doesn't come inside, it's meters before it is reached. Since we have used shortest possible, it's all going to go by the shortest possible route nearest to that particular hole. Okay, big so it can enter the hole. That's how drill. Okay, perfect. Let's look at the output and close the session. Show this output, and you get cycle. Cycle 200 is set here. A particular plane. Again, the plane changes, and the cycle is called again here. Okay, so we are now using the cycles for our drilling. You can also just go here into the function. Look, machine doesn't support cycles. Okay, so I'll say don't cycles. Run the calculation, generate the G code. No longer cycles. It's all XYZ, XYZ, XYZ. So simple mimicking of the cycle using the G1 method of SolidCAM. Okay. This is how we do multi-axis. I think we have almost everything that's available in SolidCAM 5-axis today. Like I said, if you have got questions, because I know it's too late now at the moment to ask and answer, you can write to us at email ID, and if you have got any issues, let us know. Download the software. Let us know once you have downloaded. We can arrange an online training for you. We have got several sessions running in India, so you can join one of them, and you can experience how powerful the software is, right from 2.5D milling into mill-turn, including full 5-axis. Right, I think there are no more questions in the session. I will call the session off. Thank you very much for attending this webinar, patiently listening. It's more than 2.5 hours. I understand it's a lunchtime for many of you, but thank you very much from the bottom of my heart for looking at this webinar. Let us know if you have any questions on my email address, which is right there on the screen. The webinar recording will be sent to you within 24 hours of today. Okay, thank you very much and take care.